acting on x is z belongs to 0, 1 to the power of n minus 1 to the power of xz z kit divided by 2 to the power of n. Okay, I think I think we can start again. Yeah. So right. So where are we at? Yeah, this is a circuit we have. Okay. So let me save this. I think export this as an image. If it loses, yeah, it is saved. Right. So this is a quantum circuit. Initially, what we have n0 registers, that is a query registers, one ancillary register. So that is our input psi1. So this is where input psi1 is there. Okay. Now on the query register there is a n Hadamard's and one Hadamard acting on the ancillary register. Okay, that is what I have written in the second line. Okay. So where is psi1? Psi1 would be here. Okay. So I can easily get what is psi1 would look like. As we know, Hadamard, n Hadamards acting on n0 registers would give me output of equally probable quantum states. Okay. So that is what psi h acting on this. So just to replace this here, you would get what is the psi1 would look like. Okay. Right. So now h acting on 1 gives me just a equal superposition with a negative relative phase. So I will have that also, and I will have a psi1 carefully written using the Hadamard action individually. Okay. Now on the psi1, as per the circuit, unitary function is acted and which gives me psi2. On psi2, Hadamard only on the query part acts, gives me psi3. Okay. So now let's find out what is psi2 would be. Psi2 would be unitary function acting on the psi1. We have seen yesterday unitary function acting on such psi1 would simply give us minus 1 to the power of f of x added into the entire expression. Okay, that's all. There is not much difference. Now knowing psi2, I want to find psi3. Okay, what is psi3? Psi3 is n Hadamards acting on query part, identity acting on ancilla part. You go back and see n Hadamard acting on the query part, okay, and nothing acting, that is identity acting on ancilla part. Okay, so now very good. So yeah, here it is, this equation. Now as we know, right, h acting on x gives me this for some generic x for n equal to 1. For any n, h acting on x could also be written like this, any generic. So let's replace wherever there is a h acting on any generic x, replace that with this. Okay. So basically what we would get is psi3 would look like, okay, let me write down carefully, not missing anything. Okay, first I'll have a summation over x which belongs to 0, 1 tensor n. Okay, what else is there? I have minus 1 to the power of f of x minus 1 to the power of f of x okay, I have to refresh, cancel. Wait a minute, minus 1 to the power of f of x, okay, divided by 2 to the power of n, that is what I have. Okay, so this one I'll bring it here, and okay, so h acting on x gives me this entire thing. Okay, let me put that as it is. Summation over z belongs to 0, 1 to the power of n, okay, minus 1 to the power of x into z, z cat divided by 2 to the power of n, okay, so and then follows by 0 and 1 divided by square root of 2, okay. This is what the psi3 is looks like for any generic n number of query registers, okay. So the summations, there is a x summation, there is a z summation, okay. So the x summation, x value doesn't depend on z, z value doesn't depend on x, so I can just interchange the summation as per my wish, okay. So let's do that. Z belongs to 0 comma 1 to the power of n tensor, okay. X to the belongs to 0 comma 1 again to the power of n tensor minus 1 to the power of f of x plus x into z, okay, right, divided by just 2 to the power of n. See, now there is a 2 square root of 2 to the power of n is there, square root of 2 to the power of n is there, both multiplied, it gives me just 2 to the power of n multiplied by z cat 0 minus 1 divided by square root of 2, okay. This is what psi3 is looks like, okay. Now psi3 looks like this. Now basically if you just take x and z, the whatever it is there, what I mean here is x could take values 0 0 0 n times, so on 1 1 1 n times. Similarly z could take values 0 0 0 n times, 1 1 1 n times, okay, n times. Whenever I am saying xz, it's nothing but x1 multiplied to z1 plus x2 multiplied to z2, x3 multiplied to z3 up to xn multiplied to zn. Why I am saying, okay, we just derived that earlier. If you see, okay, you just see here, x acting h acting on x1, h acting on x2 gives you what? See, summation over z z1 z2 minus 1 to the power of x1 into z1 plus x2 into z2 divided by square root of 2 square z1 z2 ket. That is what we'll get. So that means here also, right, x into z is, it is just like a two vector product. Let's say there is a vector r1 which looks like xy plus yj plus zk, r1, right, x1 y1 z1. Let's say another vector r2 x2 plus y2 plus z2k. Now if you ask what is r1 dot r2 would look like is x1 x2 plus y1 y2 plus z1 z2. That is a dot product. And by the way, the x absolute squares, absolute values only we have to take. So that is what we mean, right? So same here, you can just say it is a dot product between a kind of a two vectors, okay. They are not literally vectors, they're something like that, okay, right. If you find it difficult to put a vector over it, you can say this is some kind of a capital X, capital Z, where X represents set of X1, X2 and so on, and Z represents set of Z1, Z2 and so on, Zn. Okay, the moment you write it makes sense, okay. Now let's try to analyze the psi3 carefully, psi3 carefully, which has what psi3 has. Psi3 has two summations, one is z, another is x, both belongs to same kind of basis, minus 1 to the power of f of x plus x into z, okay, z cat divided by 2 to the power of n. This is the psi3 we have. Okay. Okay, I'm sorry. I forgot. Every time we forget the ancilla part. We should not do that. This is the final output. Have we forgot ancilla earlier? No, we have not. Okay. Now try to analyze the query part only. What is the query part? Query part is this one and its corresponding amplitude, which is multiplying, and amplitude has some parity which is dictated by the product of x and z, and also f of x would dictate. Okay, right? So very important. Let me write down the query part of psi3. Okay, let's take that, which is minus 1 to the power of f of x dot z. Okay, z. Okay, I don't need to write z, multiplied by 1 2 to the power of n. This is the query part. Okay, query part, amplitude of query part, you can say amplitude. If you want to also want to take a query part would just this one. If you just take only amplitude, only this. Okay, right? So this is the amplitude. Now what is the state of query, in what state it is going on or it is going to fall, it is dictated by this probability amplitude, you see. Okay, let me come back and give an example of a quantum state being alpha 0 plus beta 1. When I make an observation on that quantum state, it is going to fall on to 0, falls to 0 with respect to alpha square probability, falls to 1 with respect to beta square probability. That is what I mean when I make an observation. Okay, right? So now when I make an observation on the query part, let's say query, what are the query part would look like? Query part can look like all zeros, or it can be all zeros. There is only one at the last. That one can get into any place. Okay, there are so many such things. And all ones. Okay, how many such things are available? 2 to the power of n states are available. 2 to the power of n states are available. Okay, cancel. Okay, wait a minute. 2 to the power of n such states are available. Now, if I make a observation on Z would lead the system of query registers to any of the above states. What are these states? Okay, anyone, or it can be combination of all of them. Okay, right? So let's take a case where, let's say, Z observation, if you make, okay, it falls to 0 0 n zeros. What I mean by that is, let's take, very careful, this is very important. Or if I make observations on query register, okay, where is that circuit? Okay, I'm making a on the query register, I'm making an observation, the top one. Okay, in that case, let's say it falls to all zeros. What I mean is, which implies Z1 is 0, Z2 is 0, Z3 is 0, and Zn is 0. Okay, right? All of them are becoming zeros. Now get back to the expression. This is an expression. When z is equal to 0, x into z is not going to make any difference because z's are all 0. X multiplied to 0 is 0. So what is I am left with? The query part. Query part is left with is minus 1 to the power of f of x divided by 2 to the power of n. Okay, z 0 0 n. Okay, so this is the query part would look like. Okay, fine. Now let's analyze this part. Okay, remember x also takes like 0 0 0 0 n times. Okay, so on 1 1 1 n times. X also looks like this. X states. Okay, now when I say minus 1 to the power of f of x means, okay, right, f of x means minus 1 to the power of f of 0, minus 1 to the power of f of zeros. Okay, right? So when x takes this form, all zeros. When x takes this form, minus 1 to the power of f of 1 1 1 1. Okay, this is what I have. Fine. Now it's difficult to understand for n generic case. Let's choose for a simplest case where n equal to 2. It's easy that way. Okay, so n equal to 2 means x would take 0 0 0 1 1 0 1 1, which implies f of x is 0 0, f of 0 1, f of 1 0, f of 1 1. Okay, so these are the four cases we have, right? So now I want to find minus 1 to the power of f of x divided by 2 to the power of n value, because this is the amplitude which is multiplying to the quantum state. Okay, which quantum state? In this case z, where it is minus 1 to the power of f of x 2 to the power of n 0 0, because z is 0 0. In n generic case, z is all zeros, right? For n equal to 2, I have taken z is 0 0. Okay, now minus 1 to the power of the overall amplitude. Let's find out summation, right? There is a summation. Okay, summation is also there. Where is that? Yeah, see, summation is there, this summation. Okay, so summation over z, summation over x is last because all x's are zeros, minus 1 to the power of f of x 2 to the power of 2 0 0. Right, now I am trying to find, okay, z belongs to 0 comma 1 tensor square, huh? So which belongs, so which is equal to minus 1 to the power of f of 0 0 plus minus 1 to the power of f of 0 1 plus minus 1 to the power of 1 0 f minus 1 to the power of, okay, minus 1 to the power of f of 1 1 divided by 2 to the power of 2. This is the amplitude of 0 0. Okay, now you come back. Let's say a function is balanced. Now discussion. Okay, if f of x is, let's say, take constant case first, like let's take constant, which implies what? All f's are or zeros are 1. Okay, let's say all of them are 0. In that case, what I will get? minus 1 to the power of 0 is just 1. So I will get 1 plus 1 plus 1 plus 1, that is a 4. 4 divided by 4, which is equal to 1. So the probability amplitude is 1, which means the state 0 0 exists with 100% probability if f of x is constant, taking values zeros. Okay, now let's take f of x constant and takes a value of 1. In that case, let's analyze this one itself. Okay, so now the amplitude would be this amplitude would be minus 1 to the power of 1 plus minus 1 to the power of 1 minus 1 to the power of 1 plus minus 1 to the power of 1 divided by 2 to the power of n, which is 2 to the power of n means 2 to the power of square. So which is minus 4 by 4, so minus 1. The amplitude of, okay, z 0 0 is minus 1 amplitude. So amplitude means 0 1, minus 1 means probability is square root of amplitude, which is again 100%. Okay, so therefore if the function f of x is constant, okay, then you can say the output state is always falls to 0 0. Okay, you can do other way around. If you get the output state or a query register, if you get query register falling to 0 0 with 100% probability, okay, with 100% probability, right, then you can say a function is constant. Okay, let's choose the other way around. Let's say balanced case, we have a probability amplitude like this, right? F of x, f of 0 0 plus minus 1 to the power of f of 0 1 plus minus 1 to the power of 1 0 plus minus 1 to the power of 1 1. Okay, so this is a probability amplitude. Okay, balanced scenario, balanced case. Let's balance means what? Half the time it is 0. Okay, let's say half the time 0, half the time it is 1. Okay, now as per the above, what you get? 1 plus 1 minus 1 minus 1 divided by 2 to the power of n. What do you get? Cancels. The probability amplitude is 0 for which state? Okay, for 0 0 state, which is 0 0 state, which implies if you get output of query register, okay, anything other than z state 0 0 state, then which implies then z could be either 0 1 or 1 0 or 1 1. Okay, so the conclusion you can draw is you measure, therefore when you measure a query register, query part of psi3, if the result is anything other than 0 0, you can straight away conclude that the function is balanced. Okay, very simple logic. Okay, You measure the query part. You measure the query part. If the query part is all zeros, then you can simply say the function is constant. If not, it should be something else other than state. So the function is balanced. So that is what Alice does. Alice sends the entire system of numbers in the quantum form to Bob. Okay, right? Bob measures and he sends this output psi3 state, and the psi3 she studies. Out of psi3, the Z state, okay, Z state could be a combination of many possibles, but if the Z state happens to fall onto all zeros, that means the function is constant. So that is what the mathematics states. Okay, states. In this way, Alice would easily find out in one singlet state, one single iteration, she will find the function is balanced or not. Okay, right? So yeah, right. Okay, so if somebody has any doubt, please check, please let me know. Right, I can summarize slowly if you want. Okay, right. So here if you see, repeat the conclusion again. Yeah, right. So Alice creates a set of numbers into a quantum state, sends to Bob. Okay, so where the Alice is sending, this is the point she is sending to Bob. Okay, until this point she has a control. Okay, now Bob has an ancilla states 1 at Hadamard gate, feeds that to the gate of unitary function what he has with him, and he gets a result of this one psi2 he gets. Okay, or even you can say he acts a set of Hadamards and psi3 shares with the Bob Alice, or you can say whatever psi2 he gets he shares with the Alice. Alice acts a set of n Hadamards onto the query part. She knows how many Hadamards she used in the first place. That many Hadamards she will use on the psi2. She gets psi3 and she start analyzing the psi3 only at the query part. Only at the query part she analyzes, because she doesn't need to do anything with the target or ancilla part. Okay, because with the query itself she gets some information, because the same amplitude of multiplying to query also multiplying to the target. So if she's studying a query part, actually she's studying the ancilla part. Remember that. Okay, so now as per the circuit, if you see, psi0 is 0 tensors, n tensors multiplied with another tensor product of 1 gate, n Hadamards acting on the query, 1 Hadamard acting on the register ancilla. Okay, so as per the action we can get what is psi1 would look like. Okay, right? And then I want to find what is a psi2. Psi2 is unitary acting on psi1. By the way, we have seen yesterday what is the unitary acting on psi1 is just the only difference is minus 1 to the power of f of x coming into the equation. Okay, keep that aside. Let's try to find what is a psi3. Psi3 is n Hadamards acting on the query, nothing acting on the ancilla. Okay, now if you explicitly send Hadamard into the expression, Hadamard goes acting on the x, where x would be a combination of x1, x2 and so on up to xn. Okay, so in that case, how to know, how to get Hadamards acting on such x, I want to know. For that, you can start with the n equal to 1 case, which comes out to be h acting on x is just minus 1 to the power of xz, z cat divided by square root of 2. For any n, minus 1 to the power of xz, z cat divided by 2 to the square root of 2 to the power of n. Okay, how is this? We have already derived. It is there in the notes. You can just follow it up if you don't understand now. Okay, so where is that? It is here. Okay, wait a minute. Here. See here. So this is what I mean. H acting on X. This is what I get. Okay. Now, so there is a summation of Z. There is a summation of X, which are independent. I can just rearrange, put them together. So now if you just see for both the query part and ancilla part, probability amplitude multiplying is -1 to the power of f of x plus x z. That is the leading thing which is going to dictate what would be the probability amplitude would be. So for example, you take when x is equal to all zeros. Okay, when x equal to all zeros means x into z is not going to make any difference. Okay, right? So which means I would take, right, so here I would take z equal to all zeros instead of taking x equal to zeros. If I just take all all z equal to zeros, x dot z is not going to come into the play. What comes into the play is -1 to the power of f of x multiplied by 1 by 2 to the power of n. Okay. Now f of x is the one function which can be balanced or a constant. Okay, right? So let's say for 2 query register case, x would take 0 0 0 1 1 0 1 1 now, right? So let's say function is balanced, or sorry, function is constant. In that case, all the f of zeros or f of ones are equal to 1. So if you try to find out the probability amplitude for 0 0 cat, which is 100%. Okay, right? So when you make a observation on site 3, okay, when you make observation on site 3, if at all, if the query part falls to all zeros, straight away you can conclude that a function is constant. If not, if it gets something else, okay, if it gets something else, because let's say if it gets something else means non-balanced case. Okay, so the probability amplitude of zeros are actually 0, means it is something else. Okay, let me put into a table. Okay, let me put into the table. Okay, right? I have a query register Z. Okay, and the probability amplitude, corresponding probability amplitude. Okay, and what is the function nature? Okay, let's say I have 0 0 for n equal to 2, n equal to 2 case. Okay, the corresponding probability amplitude for this is 100%, which is equal to 1. If probability amplitude 1 means function is constant, it can be all zeros, all ones, doesn't matter, it's constant. Okay, for anything other than 0 0, it can be 0 1, it can be 1 0. Okay, if it can be 1 1, right? If any one of them is coming up as 100% probability, or any non-zero probability, 100% or non-zero, 100% or non-zero. So you can simply say the scenario is balanced. Okay, right? So only blind notion you would keep. Okay, even this is also n equal to 2 case. Only blind notion you take is you take site 3, make a observation, okay, on query part. If you get 0 0 0, if you get 0 0 0, okay, Okay, let me get back to the end. Yeah. Yeah. So the query part, all zeros, but the ancilla can be in superposition. I'm not going to do anything with that. I'm keeping it remaining same. If query part observation leads to this, which implies f of x is a constant. Okay. If same thing, if observation on query part leads to, let's say, all ones, okay, and ancilla can remain in the superposition, doesn't matter, okay, which means implies f of x is balanced. Okay, we have just seen for one of the case. What is that one of the case? Is for n equal to 2, if z falls to 1 1 after the observation, implies f of x is balanced. We just saw that. Okay, so that is a simple technique Alice is going to use for finding her, so to find the function what Bob is using in the first place. Okay, by the way, what is the advantage of this method is it's kind of a secret key. Okay, right? So Alice creates a sequence of quantum states or one large quantum state sent to Bob. Bob processes it and sends back the information. Alice knows what she has sent in the first place, right? Okay, and she knows what should be the result would look like when she makes a measurement. Okay, by knowing the result, she would guess what would be the function is balanced or not. Okay, now the third person cannot do because he doesn't have the chance of knowing what state Alice has sent to Bob, and the quantum states are so much fragile, no one, the third party cannot know what the states would look like. Even if the third party tried to know it, so Alice and Bob would know. That is a quantum key distribution. That is something else we will discuss later. But only two parties are communicating between each other using quantum states and the results. So here, see here, when the Bob sends back, Bob may choose to send back the psi2 itself, which is in a quantum form. Okay, if somebody fiddles, the quantum nature is lost. Okay, so psi2 is sent back, that means it is still in the quantum domain. So they can ensure that if the quantum nature of the transport information is lost, that means somebody is fiddled with it. Okay, right? So the function what Bob is using or not, Bob using balanced or constant, Alice would knowing it's like kind of a secret key shared between them. Without revealing what the function is, Alice would know by just doing this queries. Okay, right? So I have a summary here. I can quickly explain that. Okay, we can stop exactly at 4 o'clock. Okay, so the summary is here. You see now. Okay, so first Alice would prepare, right, a set of all zeros. Okay, so procedure I'm talking about. You forget about, like, you can go through the first few lines, you go to the procedure case. Okay, yeah, here Alice initialize all the states in zeros, and then create a superposition of query registers using the Hadamard gates. Okay, and send them along with the ancilla qubit, or let's say she sent to Bob. Bob adds an ancilla qubit which is in superposition of 0 and -1 and adds a unitary function f onto that entire state, which is the third step, and then he performs a Hadamard transform, okay, on the output of that. Okay, right? So once he perform the Hadamard transform, let's say he will get a quantum state psi3 that he will send to Alice, or he can choose to send even before the Hadamard action. Let Alice would do that Hadamard action and takes the psi3 and assess the psi3. If the psi3 falls to Z, where Z is all zeros are there, then F is a constant. If anything other than all zeros, Z state is, that means F is a balanced. Very, very simple logic. So, okay, so you can see here n equal to 2 situation I have discussed. Okay, right? For n equal to 2, if the function is anything other than 0, 0, let's say take a function is, sorry, state is Z is 1, 1. In that case, Z1 is 1, Z2 is 1. If you find out, okay, right, the function has to be a balanced in that situation. Okay, so the conclusion is, if the output is a clear 0, 0, simple constant. If the output is not other than zeros, the function is balanced. Okay, right? So if there is any doubt, let me know here. Okay, yeah, for a balanced case, probability came to 0 for 0, 0 kit. You are right, you are saying for a balanced case, I have a table now. Okay, just to go back to table here. See, you take any balanced case, which means the 100% probability is there for 0, 1, 1, 0, 1, 1, but 0 probability for 0, 0 kit. That is certain. So remaining 100% probability may share between these three states, or one of them may come out strictly. But strictly 0, 0 is absent in the output. That is the balance scenario. Okay, so it means a constant function we will get register as 0, 0. Very good. And for a balance, we will not get any state as amplitude is 0. No, for a balanced case, we may get a combination of these three or one of them. Okay, so let me write down explicitly for balanced case. Okay, the psi3 would look like this. I'll show you what I mean. There is some probability, okay, some alpha 0, 1, 0, 1 ket, alpha 1, 0, 1, 1, 0 ket, plus alpha 1, 1, 1, 1 ket, entire thing multiplied by 0 ket, 1 ket divided by square root of 2 to the power of n. Sorry, not 2 to the power of n, just square root of 2 here. This is a ancilla part. Here, this entire thing divided by alpha 0, 1 square plus alpha 1, 0 square, alpha 1, 0 square. Okay, let me write down neatly, clearly. Okay, some normalization constant. Okay, what is that normalization constant? Is square root of alpha 0, 1 whole square, alpha 1, 0 whole square, alpha 1, 1 whole square. That is what you will get. Okay, sometimes alpha 0, 1 can be 1 and alpha 1, 0, alpha 1, 1 can be 0. Okay, in that case, what I will have psi3 is, okay, 0, 1. Okay, this is the output, which means function is balanced. Okay, it can be 1, 0, it can be 1, 1. Other options. Okay, so that is a Dutch algorithm, Dutch Joyce algorithm for you. Yeah. So see, the probability of alpha 0, 0 is not there anywhere here, because alpha 0, 0 is 4, like it is becoming 0 in the first place, means 0, 0 ket is not there anywhere at all. So that the indication of function is constant or not is carried by 0, 0 ket. Okay, that's a very, very simple logic. Okay, the presence of zeros all zeros, okay, z becoming all zeros implies f of x is constant. That is simple logic. You don't look for anything else. If z becoming all zeros, f is constant. Otherwise, it is balanced. Okay, right? Fine. Is there any other questions? Let me see. Okay, let me save this quickly. Export it as image. Yeah, it is saved. Right. So my notes has everything neatly done. I am not sure how much is explained in the note textbook. So I tried myself to make it more simpler. Okay. You please follow through the entire notes. You would understand. Or you can also follow through my handwritten scribbling. This is also not too small. Okay. Right. So some of the things which we lost in other notebooks, but I ensured that everything else comes into this handwritten thing. So you will understand that. Okay. Yeah. Maybe I'll add Dutch DUTSCH Joysa algorithm. Okay. Okay. Save export image again. Yes. Fine. Yeah. Okay. Right. So let me summarize. Okay. Parallelism means multiple function values finding at a time. Parallelism means Dutch algorithm means not only function finding the functional values, also finding the sum of the function values. Like second level. Third level, Dutch Joyce algorithm, finding the functions, finding the sum of the functions. Not only that, let's say function somebody uses a balanced or constant, that we can find. Okay, right? Okay, so function would take either 0 or 1. Let's say it takes all zeros, means a constant. The function takes all ones, it is again constant. The function sometimes takes 0, sometimes takes 1, but equally it takes with 50% chance, then it's a balanced function. So what kind of a function is that? If you know, it is more handy, right? Knowing the function values is handy. Knowing the sum of the function values is handy. Knowing what kind of a nature of the function, whether it's a balance or constant, that would be more handy. So which takes one shot, one single shot, you can get all these things if you use a Dutch Joyce algorithm circuit. That is a conclusion for today. Now, so you see, in the classical communication, you need a multiple iteration to do these tasks. Okay, so that's why there is a long computation time here, less computation time here. Even though you repeat the same quantum circuit execution several times, even that is much faster than classical computing, which is doing few iterations. Okay, because the quantum systems are very, very hyperactive. Fine. So now in the next session, what we will do, we will go for Bernstein's Vajrani algorithm. There, we would see exactly how quantum algorithms are much faster than classical algorithms. Okay. One simple task we'll take, we'll do that. Okay. Yeah, I hope today's is more understandable. It is a lot of zeros and ones playing around. So the catch is just here. What is that catch? Okay, from the notes, the catch is Hadamard acting on X state. The next line, this is the catch. Okay. If you understand this one page, I don't know which page is this, page number wise. Okay, if you understand this, okay, everything is straightforward. Fine. So come up to here, please make yourself clear. Okay, take a cup of coffee and carefully see, you will understand that Joyce algorithm is that. So all other algorithms of quantum computing in a way built on this thing. So if you understand, it is much easier. Fine. Okay. So I'll stop here. If there is any doubts, I can take. My hand notes, sorry, my lecture notes, this is my lecture notes. Na? This is already shared on Canva, right? And this I'm going to share on the Canva handwritten thing, because some steps, small steps are not there. Maybe those things are there in my handwritten running notes today. Okay. Or if you watch the video, maybe in a fast phase, what is there in YouTube, you would understand quickly that also. Okay. Right. So see you tomorrow. Bye bye. I will hand it over to the academy at MNIT Jaipur. Yeah, what is the purpose to use this algorithm? Like I said, okay, one purpose is somebody else, like my counterpart is doing something. Without asking him what he's doing, I will get what he like is like his task, the information is doing. Okay, because if I ask exactly what is doing on an open field, anybody can get what we are planning each other. So let's say I want to ensure some security, so in that case this is a very good tool. Okay, right? And another thing is, see, computing is nothing but finding function values or finding the nature of the function. To find the nature of the function, if you need so many steps, so much iterations, means so much of computation time. If you do all those tasks in one shot using quantum computing or quantum algorithms like Day-9, then your computation time is reduced. Okay, right? It is, yeah, it is a kind of cryptographic algorithm. Somebody was saying here, Rajkumar, I think. It in fact led to the actual cryptography. Yeah, yeah, right. And moreover, more than cryptography, it is like reducing the number of iterations, reducing the usage of resources or time resource, like time duration, to much smaller computation time. That is the main catch. Like I said earlier, parallelism means, quantum parallelism means multifunctional values finding in one shot. Dutch algorithm means find the multifunctional values, sum them up, together you find in one shot. Okay. And Dutch is, if somebody is using a function anywhere in Dutch or parallelism or Dutch algorithm, if that function happen to be a constant or balance, you can find the information, nature of that function also in one step. So all those things in one step, like three birds in one shot. So in a way, it is a time reducing or computation time reducing algorithm. Okay. Does it provide solution to NP complete? Okay, there comes a powerful question. Yeah, okay. Yeah, complexity class again. The computer scientist people will not agree. The moment you bring in quantum algorithms or quantum way of finding solutions, there is a chance to reduce the NP, like hard problems, to much smaller domain, because there are few problems can be solved by quantum computing, so which was not possible without earlier classical computing. So there is some change. Okay, so there is a bounded quantum BQP class. So which BQP class is there, little bit larger than NP class or NP hard or NP complete class. So quantum is adding some extra essence, means extra easiness to finding the NP hard problem solutions. Yeah, there is some positiveness is there. So that classical computing scientists would not agree, because you are going to prove NP hard problems you are going to solve using quantum computing. So which is in the first place is impossible. That is what their intention, or that is their understanding. But using quantum, it can be solved. That is what quantum supremacy. Okay, Google has showed something which takes about 10,000 years time, done in 30 minutes using quantum computer having 54 qubits. Okay, so which was thought, let's say 10,000 years for the time being, for us to solve something, a task, is a impossible task. Like it may fall into NP hard or NP complete. Okay, so that is now being dealt with quantum computing. Okay. Okay, is it much secure? Of course, anything you send by quantum information or quantum state, it is going to be very secure, because the moment somebody tries to fiddle with the ongoing quantum information, it loses its quantumness. The moment it loses quantumness, the third person cannot add a quantumness to it, or if he tries to add, he can't exactly add the same quantumness which is there in the first place. Okay. So the two parties which were doing communication between them using quantum channel, so they easily can recognize some third parties fiddling with their communicating channel. Okay, so just by knowing somebody is there, you can just disregard that channel and recreate new channel. So that is a quantum key distribution or quantum cryptography for you. So it comes as a part of quantum cryptography. Either whether it's there here or not, I don't know in this particular QT-05, but that is what the QCAD is. Okay. Okay, so does it NP? Okay, is it possible to run its magic on IBM platform? Yeah. So IBM platform, yes, of course, it is there. Okay, algorithms are there. Maybe I can show you quickly. Okay, I hope it doesn't consume others' time. Okay, okay, just a minute. There is something called Q Universe. It is just like IBM. You create your account, like I told you, I think last sessions. Okay, and create account and log in. So inside the composer, okay, I showed you last time. Wait a minute. Let me share my screen. So you can execute. Okay, wait a minute. Share the screen, share. Okay, this is the website. This is the Q universe. If you want to implement, let's say, algorithm, Dutch Joyce algorithm, go to algorithms. Okay, see, Dutch algorithm is there. Just load the circuit. Let me load the Dutch Joyce algorithm. It is loading for 2 qubits. You see, 2 qubits, 2 query registers. Okay, so then you would read the result. From the result, you can make whether function is balanced or not. Okay, right? So even in the IBM composer also you can load Dutch Joyce algorithm, but I don't think so ready-made algorithm is there. You can create your algorithm by adding two more registers. Okay, you can add register, you can add the circuit, whatever I was saying earlier, this circuit. Okay, and then make the measurement, and you are just like playing Alice and Bob together. Okay, Alice would have first 2 registers in the control, Bob would have second or third register in the control. So they process the information and send. And when you measure in the place of Alice, you make the measurement, you will get the result that you see here. Based on output falling into 0, 0 only, you would assess the function being used is a constant. Okay, you can do that. Of course, you can do. Okay, so any other questions here quickly? IBM platform, yes, you can do. Can you write the position of Alice and Bob on the circuit made by you initially? Yeah. Yes, I think I can do that for you. Let me stop sharing the screen here. Okay, let me share the screen here. Share screen, entire screen. Hide. Can you see my screen? No, I have to stop sharing here on the other system. Okay. Yeah. So okay, Somebody was asking where is Alice and where is Bob now. Okay. Right. This is Alice. Okay. This is Bob. Right. X, Y, X, Y plus f of x. This is unitary function. Alice, Bob. Okay. Right. Alice creates this, sends to Bob. Bob has this entire thing with him. The gate is with Bob. Okay. Now he also has a ancilla. Okay. He takes this input information and feeds to gate what he has with him. Okay. And right, he will get this output. Right, from the gate he sends the output to Alice. Okay. Right, he may keep this ancilla information with him, doesn't bother, or he can send his information also along with the ancilla to Alice. So that state psi3 is okay. At this point he can choose to send psi3 or he can choose to send psi2. So if we choose to send psi3, which is looking like z and x minus 1 to the power of f of x plus x into z 2 to the power of n. Okay, z 0 minus 1 divided by square root of 2. This is the state he is sending, or Alice is going to have. She will assess this entire part and gets zeros and concludes f is constant or any other implies f is balanced. Okay, right? So this is what you would have. Okay, so let me export this as image 12. Okay, fine. Yeah, any okay, perfect, thank you. Any ideas about quantum image processing and how to implement it, sir? Yeah, see, image processing is okay. Image processing is nothing but taking a large image and then classifying it or distinguish, making some sections. Okay, so a lot of data is there, right? So that data, maybe classical computing, even GPUs are struggling to do. So that information you convert into quantum information, that is called embedding. You can embed in terms of amplitude, you can embed in terms of rotation angles. Okay, so angle embedding, amplitude embedding. Okay, there are so many different embeddings you can do for a quantum state and feed it to a quantum gates like this, process simultaneously all the information at a time and draw a conclusion in one shot. So that is a quantum image processing for you. So it needs advanced level of understanding. Okay, we can build from here, right? So I hope I'm not an image processing person, but it's like processing a lot of data using quantum computing or quantum circuits. Could you please suggest some resource for using quantum computing concept of implementing the neural networks? Oh, okay, that's a good question. Right, so there are so many online platforms for neural networks, quantum neural networks. Penny Lane is a very good platform. Penny Lane and Q Sharp. Okay, those things you can check, or you can start with the quantum machine learning by Peter Wettick. Peter Wettick. It is available online, I think. Any quantum machine learning algorithms, even IBM has a quantum machine learning algorithms. So you can go through the initial tutorial and you can do that. Okay, IBM has good resources, documentation. And this Q universe of Indian government prepared by CDAC Bangalore, it also has very good documentation. You can start at that point, very initial basic points. The Q universe, please create an account, everyone. In communication, possible to implement, yeah, that is quantum cryptography for you. That is slightly different from whatever circuits which we discussed. Okay, in quantum cryptography, you are going to create a security key at multiple locations using quantum channels. Okay, the third party cannot get to know that security key because the quantum channel is used as a means to create. So that is a quantum cryptography. Yeah, in fact, it is done in quantum cryptography. Quizzes option, the quizzes option on the canvas is not showing. The previous attempted quiz one, what is it? Not even grades are visible. Okay, this our academy people will address this question. Huh? I have 31 years of experience on HPC. Why most of the areas considered nowadays are QC only? Is it a hype? Yeah, I think it's like, see, it's psychological, right? If the like classical computing scientists are having all the fun and thunder, okay, means they're coming with AI, right? AI is doing a great stuff now. Quantum computing, that is the science people, physics people, basically they're trying to steal the thunder from classical computing people. So that nobody likes, classical computing people doesn't like that, nobody wants to steal their thunder. These people are coming in the midway, so that's why these people don't agree. They simply say it is a hype. Okay, right? Like from their perspective, it is a hype. But actually, what is going on? There are problems quantum computing is solving in the first place. Okay, right? May not be real world straightaway applications, but when it takes security, quantum security, in next 10 years, let's say somebody gets hold of 10,000 qubit quantum computer, the existing RSA encryption is gone case. It is not going to be secured. So somebody has to come up with other security protocols. So that is what post quantum cryptography. Okay, I would say it is not hype. As a science person, it is not a hype. So the same criticism was there for quantum computing for the past 40 to 50 years, because initial days when people are proposing qubits, classical computer scientists are saying it is not possible to realize. These people have realized now, started doing computing, started doing teleportation, started doing entanglement distribution. So okay, so all these things being done in front of us. So it is not just a hype. Hype means something like peaks and then disappear. Okay, for the 30 to 40 years, it is going up and up and up. Okay, so that means it is not just a hype. So it is easy to say it's a hype. Okay, it is easy to. Hello, hello. Yeah, I hope now my audio is coming out. Power is gone. When power came back, I think that is the issue, right? Yeah. Okay. Yeah. Fine. So that's all from my end. How many? 20 minutes more over 4 o'clock. Okay. So see you tomorrow. Is QC is a feasible state? I don't know what is that question is. Is that quantum computing is feasible? You mean yes, it is feasible. Of course. Yeah. Okay. Thank you everyone for listening. See you tomorrow. Bye bye. Akkad, yeah. Thank you. Okay. So maybe I think I can exit.